talking about log properties, right? As I don't know if you want to call it like a counterpart, right, to some familiar exponent rules, right? So, excuse me, for exponents on the same base, if you want to multiply, you can combine the powers by adding the powers. If you want to divide, you can combine the powers by subtracting, top minus bottom, right? Or raising something that has a power to another power, you multiply the exponents together to combine those. Well, since logarithms are exponents, in a sense, right, what a log does is tell you about a power that you know maybe don't know, or let you see it from a different perspective. Properties for logs work in kind of a related way then. If you're taking the log of a product, you're again finding the exponent that you would need on whatever the base is to obtain that product. Well, you can split those up then, split those factors apart. It becomes two separate logarithms, and the way you combine them is with addition, right? Because again, each of these things is like sort of what's happening in the superscript here, right? These exponents, that's what these logs are in essence. So this addition is this addition. So similarly then, if you're dividing, you can split them apart and subtract instead. And exponents, a power inside a log, you can bring down and treat it like it's a factor, like a coefficient, right? So the log of x squared, just a little bit more on that one. That's like the same thing as the log of x times x. That actually looks like it says log. There you go. Log. Well, no, there's a weird space. Okay, now it's fine. The log of x times x. Well, product rule says I could split that up by adding, but then really I've got two of the same thing. This power rule thing means that this works even when it's not quite as straightforward as a square, where I can think of it as just two copies of the same thing. But it works for other stuff as well. If that exponent is negative or a fraction or anything else, it works the same way. So powers inside a logarithm, we can always kind of bring down front like that. Now again, we talked about this a little bit yesterday, but these are strange, right? These feel different. Working with logs is different than working with other stuff. So we do have to, sort of get used to that a little bit, right? And train ourselves on how to work with those, because they do work differently, right? They do all of these things, but they don't do some other things. Like, for example, logs don't distribute over, addition or subtraction in the same way that, something like that would, right? Here you can distribute and simplify. You can't do that with a logarithm. They don't work the same way. So if we've got something like a sum or difference that's on the inside of the logarithm, we're just going to be stuck with that, right? We're going to have to figure out how to work with that. And that's, one of the things that you do in sort of thinking about domain is how you, how that affects things and how that works. Okay. And then I think we did A, right? Okay. One of the other classes, I don't think we quite finished A. This was 3 times the log of x, and then the log of y. Right, so again, we've got these multiplications here. Multiplication or products turn into addition, where we break the pieces apart. So I can split 4 and x cubed and y up into sort of the 3 different kinds of things that are represented there, right? There's the pure numeric term 4, there's an x term, there's a y term. I can break those up into their own things. But the way we break them up is by, splitting it into a sum of 3 separate logs then. And then in each of those, we just want to see if we can do anything else, right? The log base 2 of 4 is 2, because 4 is 2 squared. Here you've got a power that we can bring down, and then plus the log of y, because it's just y, and I can't clean that up any further.
Why would it not be log 2?
Oh, yeah, no, it should be. I just didn't. There you go. Yeah, they should all have the same base. Yeah, thank you. The base here doesn't really matter apart from any numeric numeric terms like this, right, then the base matters. For these, it doesn't really, it just matches whatever it was to begin with, right? We're not changing that. It's all the same kind of log. Okay, and then I think I said something like, hey, go home and finish this one. We did? Oh, man, you guys were on the ball yesterday. Or I was, or somebody was, I don't know. What did we get? Okay. So addition here because of the product. Subtraction here because of the division. Right? So log of e squared plus the log of x to the fifth minus the log of y cubed. And then each of those we can go a bit further. The natural log of e squared. So, this is log base. Okay, you can't read that. This is log base e, right? So the question is how many e's are in e squared? Of course, you can do that with a calculator too. That's 2. And then with each of these, we've got an exponent that we can bring down. With no context or meaning or any information or anything else about what x or y are, I can't do anything else with this, right? It's in the lowest, simplest terms. So that's this thing sort of fully expanded. Okay? You feel okay about that? Yeah? Okay.
For the 2, if I put like 2 times L and D,
so it is 2 times ln of e, but the ln of e is 1. Uh-huh. So yeah, you would want to go further and sort of simplify that all the way down. Yeah. Say again. Like here? So it is in that, like, what you're doing here is bringing that 2 down, right? If you're going to think about it this way, so if we think about it directly, like sort of definition version of the natural logarithm of the power of e, those are inverses, they're going to cancel, we're just going to get whatever the exponent was. Or think about using the power rule, you bring the 2 down, that leaves the natural log of e, but that's just 1. The natural log of x, well, this is a log base e of x. I don't know anything about x except that it's like a variable, right? So this doesn't simplify any further. If it had been the log base x of x, that'd be 1, right? So it's because, this is asking, this is a log with a base that doesn't match what that thing is. That's why it doesn't simplify any further down. Okay? Okay, cool. Okay, so that's expanding. Right, taking a single messy logarithm and breaking it up into simpler, smaller pieces using these log properties. We can also condense by, basically going the other direction, right? So kind of working backwards. So these two, we're starting with a big string of several logs, right? That looks kind of like where we ended up on the previous couple. And your goal then is to mush them all together into a single thing, right? So the answer here is going to be, hang on. A log, it's base 3 of, I don't know yet, but all that stuff mushed together, right? So it should just be a single expression that we get from combining all these things using these log properties, but the other direction, right? So kind of in reverse. So let's take a couple minutes. You guys give those a shot. And it may help to look at the couple that we just talked about / did yesterday, and think about kind of working backwards, right? Start at the bottom and work your way up. Since that one is subtracted, right? Okay, so think more about the sign part of it. So like, you could rearrange those things. The things that would need to be, like, stay the same. This is positive, this is negative, this is positive. Like, if I'm moving around, it doesn't matter where I put it, it's still gonna be minus 2. So think about what that would mean for, how we can. Okay? Yeah. Very nice.
Does it like matter the order? It's like, that's what I got.
The order is not that hard, it's like a 4 sequence.
So like, all the minuses will go in one row.
The signs of the important part of the order.
Okay.
Okay.
It needs to go up here.
Yeah.
So it doesn't
The sign matters more than the order, right? So you can rearrange those things.
So that's, it's been one of It's log based, it's log based.
Okay, so the base is 3, right?
It just.
The base being 3 just means the base is like, so like, anytime you're in log, you're at base 3. That's the only reason, or the only way we can make an impact on it. So, this doesn't turn out here. Okay. Okay. Yeah, so like, this would just be it, right? Like, there's no power. It doesn't turn, right? It's just all the way.
Oh,
Next piece is to go with the answer like 3.
I wasn't even here yesterday, so I was just so confused.
All of us got a different answer.
The term configuration is so
I should have been doing it to positive.
So, the sign right.
So
Negative 5.
literally everything.
They should have been flooded as well. Is this never gonna touch that? Line where that's at.
On a order,
Because it moves to the left.
doesn't matter.
Then when I crash it, it's gonna be so I obviously have to do something about it.
Yeah.
It's dead.
Oh. This is the example for A. What's a good place to start here? Okay. Our rule says exponents become coefficients, or if we go the other way, coefficients become exponents. So 2 times the log base 3 of y is the same thing as the log base 3 of y squared. Okay. Now, I've talked with several of you like individually about this, but the order that these things are in doesn't matter so much as the sign on them, right? Like I can rearrange these things, but if I do, this term has got to stay positive regardless of where I put it, right? This one's got to stay negative regardless of the order I write them in. So if I wanted to, swap these around, that's fine. That's not changing anything so long as I keep positive things positive and negative things negative. Otherwise, I'm changing it, right? So with that in mind, when we look at these, what's going to happen is that terms that are positive, and this one is, right, the leading one, it's just, we don't write that leading plus sign, but that term's positive as well. When we combine these, anything that was positive ends up in the numerator, and anything that was negative is going to end up in the denominator, right? Adding two logs means you're multiplying the arguments together, right? So x times z to the fourth. Subtracting means you're dividing by that thing. So over y squared. If you want to think about, like checking, right, you could sort of reverse that process and see where it ends up. If I take that thing and, so let's just, say we're going to check. Maybe we feel more comfortable with the expanding idea. X z to the fourth minus the log of y squared, right, splitting that division. And then multiplication there, so add. And then you can do the power rule thing to bring the exponents down. It's in a different order, right, because of the way I've decided to write things here. But it's the same thing, right? This is positive, this is positive, this is negative. Same thing's true of what we started with, right? Okay. Questions about that? We feel okay about it?
I don't understand why y squared is the and not being multiplied by.
Okay. So here's another way that we could, maybe look at this. Instead of trying to sort of deal with the thing altogether, let's just look at those terms, right? Forget about the other one for now. We'll come back to it. It's something, a log minus another log, right? So division. So it becomes x divided by y squared. Plus, well, now we've got addition, right? And the way you handle addition with logs is that you multiply. But then since we're multiplying a fraction, by a whole number basically, right? Treat this like z to the fourth over 1 if you want. It ends up moving into the numerator. When we sort of, clean things up, right? This part's just making it look nicer. Okay, does that help? Yeah, okay, cool. All right, how about B then? Okay. Okay, combine them how? Okay, 5 times 3. Yep. Okay. What else? What can you do with this? Okay. And also, okay. Log of y, let's leave alone for right now. Here we've got another coefficient, so that becomes z to the fifth. If you haven't, had to like write z's in math context before, just make sure you can tell your z's and your 2's apart, because sometimes z's turn into 2's and then weird stuff happens. Okay, so there's, a step, right? We've done some stuff. This is a write down as much as you need to keep track of what's going on, right? So do it in as many or as few steps as you need. What can we do here? Division, right? So that's going to turn into the log of 15 over x squared. And then what else? I mean, you can just keep rolling these things together, you know, from left to right. 15 over x squared y, right? Oh, sorry, I left that guy out. Still there. So 15z to the fifth over x squared y. You know, once we finally combine everything into one. But again, look at what happened. All the things that were positive to begin with ended up where? In the numerator, multiplied together, right? 5 times 3 times z to the fifth. That ended up being the numerator. All the stuff that was negative to begin with ended up in the denominator. What are logs again? Yeah, right. Yeah, this one's base 10, but in general, logs are exponents, right? They're powers. I don't know which version of that you're happier with. Logs are powers. So if a log is negative, that means the power is negative. Where do negative powers go? In the denominator, right? Because the negative power means take the reciprocal. That's why when we do this, all the terms that are negative end up being in the denominator because they're negative exponents, and that means, hey, put that thing in the denominator, right? Like, take the reciprocal of it. So they all end up here, and all the positive things end up in the numerator. Okay? Help maybe kind of make the connection of what's going on there. Okay, cool. So you'll see some stuff that's, you know, asks you to just do these things kind of directly, right? For seemingly kind of no reason other than to like practice, you know, using these properties and rules. Generally, that'll say, you know, here, take this thing and expand it, or take this thing and condense it. That pretty much covers the stuff that's on this week's homework, right? Yesterday we talked about, you know, the way the homework's set up for right now. There's only the one assignment due this week because the other one, I'm not totally sure that we're going to be quite done with everything by the time we get there. And, you know, it's more difficult. I want you to have more time with it. But that's over solving equations. This stuff will sometimes come up in the context of solving an equation, right? So we might need to lean on some of these from time to time to, you know, get something to a place where we can work with it and solve. Okay? So the upshot of all that is that you should be in very good shape to finish like this week's homework between now and when I see you again, right? And I would suggest that you do that. And then we'll have, you know, the rest of the week to kind of talk about solving equations. You can at least get started on that. And if there's stuff that lingers to next week, we'll have time to hit that too. Okay? Okay. So how about solving equations? So we need to be able to solve equations involving either an exponential or a log. I want to find x that makes 2 to the x equal to 16 true. How could we do this?
Write it as a log.
Okay. I could rewrite it as a log. If I rewrite that as a log, what's it look like? Log base 2 of 16 equals x. Oh, hey, we just solved it, right? X equal, like that's solving. Like, ta-da, you know, this is jazz hands moment. We did it, right? And all we had to do was rewrite it as a log. Okay, so if we've got a sort of like pure, isolated, simplified exponential expression like this, if we rewrite it as a log, then pretty much what we've done is solve it, because again, I erased it. Logs are powers, right? Logs give you a way to find a power that you didn't know before. Here's how, right? I don't know what x is, but it's the log base 2 of 16. And if I can evaluate the log base 2 of 16, which we can, then we're done, right? What is the log base 2 of 16? 4. Okay, why is it 4? Okay, because 2 times 2 times 2 times 2 is 16. Or other valid reasons would be because my calculator told me so. Like, that's fine too, right? It is 4. That means there's another way that we could have approached this that is a little bit more, again, the first step is like, hey, notice that, right? 16 is 2 to the 4th. And if I rewrite or think of 16 as 2 to the 4th, then we're asking 2 to the x, 2 to some unknown power, right? Like, what power of 2 is the same as 2 to the 4th power? Well, exponential functions are functions, and they're also one-to-one, right? So since they're one-to-one, this can only happen if these things are the same, right? Okay, now that's neat, right? It's not the most useful thing, because what if the question had been 2 to the x equals 15? Well, 15 is not a power of 2 that I'm just going to, sort of like pull out of thin air, right? I can do that with 16, because again, 2 times 2 times 2 times 2 is 16, right? And like, even if I don't, immediately jump to that, like, we can get there. The numbers are small enough, right? I could do that. Whereas that's no use at all here, really, right? I know the answer is a little bit smaller than 4, probably, but that's about as close as I can get. So this is a convenient thing sometimes when it happens, but it's not the most reliable thing, right? So if you happen to look at something and just see it and go, oh, hey, I recognize that. That's a power of 2. And I can figure out 2, 4, 8, 16. Okay, it's 2 to the 4th. So x must be 4 then, right? Like, that's great when it works. But again, it doesn't always work, and it's not the most adaptable thing, right? Would this work equally well with the thing I just wrote down? If you rewrite it as a log, what do you get? X equals the log base 2 of, oh, hey, we solved it. Don't worry about this part. X equals, this is some number, but we solved it, right? That's why I made such a big deal about the, going back and forth between exponential and log form. If you can do that, which is the only thing we needed to do here, we're pretty much good to go, right? Like, that's going to be the key step in just about everything we do here. Okay, so let's take a few minutes. You guys work on some of the rest of these. These are all, I'll just, lead with this. These are all things where you could, in theory, do this, right? Like, both sides will end up being things you could easily write in terms of the same base. So you could do that. Or certainly you can, kind of always approach it this way. So think about, what you might need to modify. You know what? Let's just talk about it together. We might need to modify, or what's going to work differently here. Okay, there's a -1 up there. Now, keep in mind that stuff we treat like it's grouped, right? So we leave that stuff as one solid piece, which means I don't really need to worry about the fact that it's a -1 yet. 3 to some power is 27. What can we do with that to, get rid of the exponential part and bring the thing I'm solving for down? Yeah, rewrite it as a log. The base is 3, so use the base 3. And, base and answer an exponent, right? So the log base 3 of 27 is equal to x minus 1. Okay, what are we going to need to do to solve then? To get x by itself? figure out what this is, and then add 1 to it, right? Move that 1 over. Okay, so what's the log base 3 of 27? It's 3. So what's x? 4.
The key is to not look at the log as like its own equation. Treat it like a number in a sense.
Yeah, right. Yes, this is just a number. Yeah. If the base and the thing inside the log are both numbers, then the log itself is just a number. In some cases, it might clean up nicely and be a, nice round number like 3. In other cases, like if this had been 25 or something, well, it doesn't clean up as nicely, right? So if I'm trying to find an exact value, I might just leave it like that. But it's still just a number. You still just treat it like a number. Yeah.
I added 1 to like 47.
Yeah, okay.
I was like, what?
So you need to add the 1 over, but you don't move it into the log. Yeah, so the log is kind of its own thing, right? So like treat that thing like it's, I don't know, sealed or something, right? Like that's its own thing. And when you add the 1 over, yeah, it's, adding 1 to that as a whole quantity. Uh-huh. Let's see. Like a 2 there, maybe? What's the exponent on here? Just that, right? Okay, so thinking about order of operations and stuff, parentheses, exponents happen before multiplication. So treat that like it's, again, sort of its own thing. Like that's a closed system. You don't move stuff into or out of that. So what should we do to deal with that 2 out in front? Instead of like moving it into the exponential thing, move it to the other side by dividing. Yeah, do that before the log. Otherwise, like in a sense, what we're doing when we do this is taking the log of both sides, kind of. If you take the log of both sides here, things are going to get kind of messy because you've got, these 2 separate things going on. You can deal with it still, but it's going to make life a little bit more difficult. I don't know. What do you think? What would be good things to do here to begin with? Okay. And then? Yeah. What we're really doing is trying to get the exponential term by itself, because once it's by itself, then I know how to think about it as a log and how to rewrite it as in terms of a log. When there's this other stuff going on around it, that complicates things, and maybe not in the way that I think it's going to work, and at the very least, it makes life harder, if not impossible. So instead, when there's straightforward algebraic stuff we can do to move things around and get this term by itself, we should do that first. Right, so add the 1 divided by 2. 5 to the x is 25, which means that x is 2, right? Which you can either get by, inspection, right? By looking at it, right? That's 5 squared, or log base 5 of 25, which is 2. again, this one, you're fine to like see this and just say, oh, x must be 2. Like that's totally okay. Don't feel like you need to write this out. But there will be a lot of times that we do need, to kind of go a little bit further because it's not going to come out quite as nicely. And that's even true if the numbers are just bigger, right? Like if this was, I don't know, 125, maybe I don't recognize that that's 5 cubed or, some higher power of it. All right. Y'all take a minute, think about part D there. What's different here? There are 2 separate exponentials, right? 2 to the x and 2 to the x minus 1. They both have a variable in them, which means I have to treat them as though they're, variable things, right? So I can't, here I had a factor of 2, and the way we dealt with it was to say, well, just divide it and move it to the other side, right? Get all the constant stuff sort of grouped together over there and get the variable stuff by itself so we can think about what it means. Here, there's variable stuff here and here. So I can't move one of them over because if I do, then, 1, how do I combine 8 and 2 to the x? And 2, then I've got variable stuff on both sides. That's going to, make things at least more difficult. So how can we combine these? Product rule. What do you do with the exponents? The bases are the same. So x plus x minus 1, which is 2x minus 1. Do it? Oh, yeah. Then rewrite it. Or again, if you see it there, then that's fine. If I rewrite it, the log base 2 of eight, right? Base, exponent, answer, base, answer, and exponent. Log base 2 of 8 is 2x minus 1. Yeah, good. So hopefully you're kind of starting to see what I mean when I say, if you can go from the exponential form to the log form, and, the other way too, like we'll get into that on Thursday, going the other way. But spoiler alert, to solve equations with logs, the main thing you do is this, only that way instead, right? Rewrite it as an exponential and like, ta-da, all your problems go away. If we can do that, even when there are variables and expressions and other stuff going on, if we can rewrite like this, that's the bulk of it. Now, what is the log base 2 of 8? So add 1 to both sides, divide by 2. Okay? good? Do we have any questions about anything at this point? Okay, well, there's two more there for you to do. Stop this. Okay. Now,